Well, hello there. Just making sure before I kick off and do anything that people can hear me. I know that there are a lot of people already in the stream. Some of you have been here for like 20 minutes already, which I was quite surprised at when I turned on the streaming software this morning and I saw there were already people waiting to watch. So let me just give it a sec. Say hi if you're in chat. Just make sure that you can. Yep. Okay. Cool. Heaps of people saying that they can hear me. Microphone volume is good. That's great. Let me just. I'm just gonna move my little face to the top right corner because I think that this will take up the least space for my slides, so that way I won't cut off any of the text. We'll see. I'll keep checking and make sure that I'm not cutting off too much of the text. I'm cutting off the edge of the word programming, but pretty sure you know that one by now. I'm pretty sure you know that that's the course you're in. Hopefully, unless you've got a mild case of cabin fever and you've locked yourself inside your house for the majority of the last few weeks and haven't gotten out at all. I'm hitting that point as well myself, actually, where I've tried to be as responsible as I can be, and I haven't really left the house since we started going online, actually. So now it's now 2.5 weeks, I think. So we'll see how we're going. Oliver Star, I actually don't think I'm putting my face on any memes today because I don't think I have any visual memes in the lectures today. I think in some of the examples I have like pop culture references, but I don't think I have any actual pictures today. Okay, so we're back into the swing of things now, and we're gonna have a rhythm now for the rest of the term because we've got 4 weeks now, weeks 7, 8, 9, and 10, that are just going to be us going through content again. I'm hoping against hope that there aren't any more sort of major university level or subject level upheavals or anything like that that's going to happen. If you've been checking your email, you will know that I think it was yesterday afternoon an email went out to everyone saying that seeing as everything has been shifted pretty wildly this term, that there's a sort of a subject amnesty happening at the moment where if you fail a subject in term 1, it won't go on your record as a failure. You'll be allowed to just take the subject again and have a second shot at it. So this is on top of the pressure being taken off by most subjects going pass fail, which is the idea that you won't be given a number grade for the subjects, and COMP1511 is in amongst those subjects. And I'm pretty sure the intention for this is that a lot of people are going to be disadvantaged. I mean, I know there's some of you there who probably aren't live right now, or maybe, I don't know, depends what time it is in the country you're in. But I know there's a lot of people who, over the last couple of weeks, had to return to their country of origin because of the pandemic to try to at least get a chance to ride out the pandemic at home with your families rather than sort of out here in Australia where you don't necessarily have support networks around you. So anyone who's in that situation, hopefully you can still access everything. I mean, it would be sucky if you got home and you didn't necessarily have access to everything that I was recording, but I think YouTube is reasonably available everywhere. And I forgot to do this for the bonus stuff last week, but I'm going to save everything that I'm doing on Echo 360 as well, so there's links, so there'll be links there, as well as the YouTube Live stuff that I'm doing right now that we can all have access to. What else was I going to say? There's a bit of content from last week, so we're back on officially this week, but last week there was a bit of unofficial content. So I ended up lecturing as much as I would in a normal week. I did 4 hours, actually did a long one. I did like a 3-hour stream on one of the days, but also one of the other lecturers, Carol Morgan, who teaches a lot of the sort of underlying thought process behind what it means to understand what your code does. And so he's been talking about a lot of the way we use comments to structure our code and the way we use comments to help us remember what our code is doing. And so he's recorded some lecture workshopy kind of things, and they're in the week 6 section alongside my live streams there. So if you want to check that out, some extra content there which would be pretty useful for people. We've been sneaking in some stuff in the comments to sort of lead into that, so hopefully when you see that you'll be like, oh, I recognize some of that stuff that Mark was trying to show us. Carol's actually the expert on that, so he can tell you more about that there. Okay, so let's launch into... Oh, there's a question from James there. How do I know if I properly submitted my assignment, or do I just have to trust the give system? Excuse me. 1 second. If you go back into the assignment spec, there's a section in there that allows you to check on a system called Git, and it'll allow you to look at all your previous submissions that you've put in. And so if you look at your most recent submission, you can actually open it, look at the code, see if that code is the one that you think should be there. If it's not the one that you think should be there, you should email your tutor as soon as you can and talk to them about it, because we do have automatically saved all of your auto tests. So if you have your final auto tests before you wanted to submit but it hadn't submit properly, and that final auto test is before the due date, we can still mark that instead. So if there's problems like that, we can still deal with it. Okay, let's look at what we're doing. So not last week, I did remember to change this word here. So rather than last week, last time that we were together officially, I mean, like after that we did cover some other stuff, but when we were together officially last time in week 5, the last things we were working on were characters and strings and structs. So characters and strings was our new variable type that allowed us to use letters. Also on the understanding that letters are represented by numbers, and so they're encoded by things that we could think of as integers, which is actually an encoding for which letter is which, or which character, because all the characters on our keyboard basically are represented as characters. We also worked on using arrays of letters that we call strings, and they're not just arrays that happen to have characters in them. They have a really specific structure that we use that has the null terminator in it, if you remember, that tells us if we're not using all of the length of the array to store our word, where does our word end? So there's a lot. You're going to learn more about that this week, because there's heaps of stuff in the lab this week about characters and strings. I also put in a little recap in the tutorial about pointers and structs, so we'll see if that's going to help jog everyone's minds. I mean, structs is really just getting into it. Pointers is more of a recap. I did do a fair bit of coding with structs in the Thursday live stream that I did. I moved one of my live streams to Thursday afternoon, because 9 AM is really early, especially if you've just been staying at home and not really getting up that early in the morning, which I have been. Gotta admit, today was a bit of a struggle, but every term that I teach that has 9 AM lectures, the 9 AM lecture always ends up being a bit of a struggle, especially the deeper we go into term, and the later at night everyone is staying up to do assignments and things. This week should be the break in between. This is our assignment break. I just sent out a course notice, but I'm not sure if it went out before the lecture started, because I just sent out the course notice about half an hour ago. That we're in our break in between the assignments now. So if you've submitted assignment 1 on time, also we've been giving out a few extensions to people who might need them. If you've had any kind of upheaval, so talking about the people who had to like travel internationally to go home and things like that in the last week of the assignment, or even just during the assignment, let us know. There's still a chance we can give you an extension, even now after the fact. And there's a lot of students who have letters of I can't remember what they're. letters of introduction. It's not a letter of introduction, but it's a letter from the student center acknowledging that you have need of special consideration. Usually they say that you have to apply for your extension before the due date, but if you really, really do need that extension, and especially if you've got special consideration, you can still apply for it now. We're going to just go easier on everyone this term because it's a little bit of a weird term, so we don't really want to push anyone to breaking point this term, because I think that a lot of people have enough stuff to worry about with the whole global pandemic thing happening. So yeah, if you need a hand, just ask for it. We'll do what we can. Okay, we use structs as well. I was talking a little bit about structs already. I've got a bit of a recap on them that I'm going to do in a second anyway, so I'm not going to go over exactly what they are. But if you want to know more about structs, there is a video now of the live stream that I did. I spent the first sort of half an hour to 40 minutes talking about the switch from numbered marking to pass-fail, and I know that this was a very difficult time for everyone. It was difficult for me as well to try to change stuff in the middle of the subject. So there's a bit of that at the beginning, but then there's I think a good solid 2 hours worth of using structs and pointers and things, and so there might be some useful stuff in there if you want to go back and look over that. This will come up more next week, I think, in your labs and when the assignment gets released, because the assignment and the labs definitely using structs and pointers. We're going to go over that more this week as well. Okay, so today we are covering memory. So, I mean, to be honest, we've been covering memory the whole time. So we've been talking about memory since pretty much the very first lecture, when I was talking about the whole idea of a computer being 2 bits, the thinking bit and the remembering bit. And then memory was everything we were doing to remember things. First thing we ever did with that was really simple, it was just variables. So stuff like integers and doubles, where we were just like, this is just a thing. This is a thing that stores a number. But now we're getting deeper and deeper into that, where we've looked at stuff like arrays, and arrays were able to take larger sections of memory. We've looked at pointers. Pointers were able to not just know that memory exists somewhere and we have a variable attached to it. The pointer can tell us exactly where variables are. We can pass pointers into functions to give us access to variables and things. The next thing we're going to do is we're going to learn how to basically take a chunk of memory and say, okay, this memory is mine. Ask the computer for a piece of memory and say, okay, now I have a piece of memory, I'm going to use it for certain things. So the interesting thing that we're getting now is we're able to actually take things like variables and structs and other things and say, give me a piece of memory, I'm going to store this this variable in that piece of memory, and then I can reuse it and things. I'm going to go into detail on this, alright? So don't worry if this is like kind of, what do you actually mean here, Mark? I'm going to show you what happens with memory, when we use functions and things, and then how we can what's called allocate memory in a way that we can keep track of it. So that's the majority of what we're doing today. The other thing I want to show you as well, because it's kind of interesting and kind of useful, is multi-file projects. So we're going to start looking at the idea of splitting a project up into multiple parts. This is going to become reasonably useful to you because the second assignment is going to be given to you as a set of different files, and we're going to learn about compiling multiple file projects in different ways. And we're also going to start introducing the idea that when we have multiple files, we might not actually give access to everything. So we might have a main file. Main file creates a program, in a sense. Well, it's got the first set of instructions to the program, and it accesses stuff from another file. We've seen this already, because we're doing hash include, we include libraries that were from other files. Now we're going to have our own files that we're including stuff from, and it'll be interesting when you see that we include some parts of the other files, but not other parts, which means we can only see some code. We'll look at that later, because I'm trying not to do too much of a bamboozle at the beginning on this stuff, and I will give you the details, and then we'll see how it all works. Okay, so quick recap, because we're going to be using these. Pointers. So recall that a pointer is a variable, and it stores a memory address. We use the and to get the address of any particular variable that we want to aim the pointer at. Question there from William. Will the second assignment be the same style as the first, where we have auto tests to guide us? Yes, it will be. So you're still going to have auto tests. It's still in stages. It's just on different content. Oh, hey, Michael. One of the tutors is... Okay, Michael, I'm going to let you answer a lot of the questions, if you're sticking around. You don't have to stick around, but if you are. Okay, so recalling that pointers are... You can think of them as a variable that points at another variable, or more specifically, a variable that points at a memory address. So if I have my big chunk of memory and all my variables are sitting in my memory somewhere, we never really know where they are. I mean, our program tries to keep them pretty close together, but after we've been running it for a while, variables might end up in different places. The pointer allows us to aim at any of those locations and then get access to the memory that was there and whatever values are stored there, and we can change the values and stuff like that. Remember, the magic symbol for the pointer is the star. We use the star to declare the pointer, and then once the pointer is declared, we use the star to kind of Google Maps the pointer. And when I say Google Maps it, I mean what you're doing is you're taking the address that's in the pointer and following it to the location that it's in, and then reading the value inside that location. We also have the arrows that we're using to access structs, and I've got structs here. Continuing with the example I did last week. I know not everyone has seen it, but if you haven't seen it, the example that I was working on last week in our bonus week, I was using stuff from Avatar: Last Airbender, because this is left over from last term, actually, term 3, 2019, when I was rewatching Avatar, and I thought it would be kind of fun to use their characters. So I did start on this K-pop thing, but then I ended up going back to my my term 3 thing. So the continuity of the story has been mildly interrupted, but that's okay. I'm actually jumping off to a different story today anyway for something else that we're doing. Okay, so a struct is a custom variable, something that we make ourselves that doesn't necessarily adhere to the variable types that we had, but what it does is allows us to piece together a variable out of other bits. So we had a name for each of the benders, we had the element that they used, how much power and health they had, and we went through this whole kind of like simulation of this fight between the element benders. And I left people a lot of challenge stuff. Fully understand if you have not done any of that challenge coding and you were coding Minesweeper instead. I feel like that was probably at that point in time something that you'd want to be doing. But if you want to, you can play around with the example from last week and the code where it's at and see if you want to take it any further. Sean's asking if standard input output.h is just a file made by someone with all the standard commands, etc. Yeah, it kind of is. It's actually just a C file. It's really full on C, if you were to look at it, because it's not really made to be that human readable. Like, the documentation is human readable, but the file itself is a little bit hard to get a grasp on. But yeah, it's basically another file, and it's one of those files, like anything that's in the angle brackets includes that we've been using is C code that has been verified, like to the nth degree, to make sure that it's something that we can just use without having to think about. Michael's saying that. Yep. Okay, cool. Yep. I think there's a lot of answers in the chat already that are covering that question. Okay. So when we have pointers and structs together, we're using the arrow. So if I have a pointer to a struct, then I use the arrow. So the pointer uses the pointy connector. There's also the dot for accessing a field inside a struct. That's if we have the struct itself. But if we only have a pointer to the struct, we need the pointy accessor. So this is what I came up with last week. I've never taught it like that before. Then hopefully that helps you remember it, because if we have a pointer to a struct, we use the pointy accessor, which is the arrow, that does a double effect that says, I am going to follow this pointer to the struct it's aimed at, then I'm going to go inside that struct to one of the fields inside, and I'm going to get access to it. So in this thing, this function here that could just display this person that is one of these struct vendors, which is one of these, and it could go grab these individual fields from it. We can use the arrow to say, this is a pointer, this is accessing a field inside the struct the pointer is aimed at, and this is the field that I'm looking at, and then print it out. So these kinds of things, it's just a matter with all this terminology. So with the star, the and, the dot, and the arrow, that kind of thing, is a matter of just sort of using them until you get familiar enough with them to be happy that you've remembered them. So if you do need to spend some time before you can remember it, I recommend writing down just sort of like the star. What is the star? It's the pointer symbol. It allows us to declare a pointer, and later on allows us to Google Maps the pointer, which is to follow the pointer to its destination and get its value out. Likewise, writing down the difference between the dot and the arrow could be quite useful as well. They're both for accessing the fields in the structs. One's if you have the struct itself, the other is only if you have a pointer to the struct. We will tend to use the arrow more often, so that's the one I try to remember. Usually I'd say try to memorize everything, but you're in a particular situation this term where your exam is going to be a take-home exam. Reminds me, I still haven't changed the course outline to reflect exactly how the course is running this term. I'll put it on my list of things to do. It's actually already on my list of things to do now that I remember it, but we'll get there. People are talking about records. I'm not sure what you mean by records, because we're not really using the keyword record at all in this subject, and so I think maybe you are talking about a variable or something like that. We'll see. Either that or using terminology that's from another programming language, and it's one that I don't use often enough to know exactly what that means. Oh, Michael's talking about that in there anyway. Okay, I think people are answering their own questions in there, so I'm going to go on and keep talking about things. Okay, so that's the recap of pointers and structs. So now we get to one of the things that I wanted to talk about today, which is understanding exactly what is happening in memory while our program is running. So there's a lot of interesting stuff that's happening. So I have mentioned this before, the idea of getting passed by value. Passed by value means that when we give a function information, so every time we call a function, right, we call the function and we open the brackets and we put variable names or values in those brackets there. When the function runs, the variables are copied by the function. The variables are not accessed by the function, they're copied. So the variable grabs the value of, the function grabs the values of its inputs and then copies them into its own memory, and they're separate copies of these, and then it works on its own variables. So when a function is created, it basically declares new variables of the types of its inputs and then starts working on them. I've got an example here that shows you an example of this in effect, the way that it works, right? So first let's look at this function. I should have put a comment on that function. We really should never declare a function without there being a comment. We're also going to assume that the function's been prototyped above, so it's got void doubler int number and a semicolon up here somewhere. So this is just a snippet. So the doubler takes a number and it says that number is now equal to double the value that the number used to have. So this is just taking a number and doubling it. Now knowing what we know about functions, you know that this is not going to do anything. And that's what this comment here is all about. Because this number that gets passed in, this x, doubler does not do anything to x. So doubler does not have access to x, and it does not change x. What it does double is number, which is here. Number is its own variable that gets created from scratch when the function is called, which is here when doubler x is called. I wonder if you can... There you go. I'm just going to move that away for a second so you can see the text. Then again, top right corner, I think I haven't put anything super important in there yet, so that'll be okay. So, people are asking about arrays in functions. I'm going to get to that. I actually have slides on that. So it's similar to what Michael's saying there, is that the arrays are passed in a particular way. Wait for it though, I am actually going to tell you about it. Okay, so the milkshake game is asking an interesting question. So if we had an x here and this was called x as well, why doesn't it cause a problem that there's two variables of the name x? The trick is that one variable lives between these curly brackets and the other variable lives between these curly brackets. Those are completely separate spaces. And because they're completely separate spaces and they can't see into each other, they don't conflict. Because there's no place anywhere in the program where there are two declarations of the same name, because they're in completely different spaces. Let me show you that, right? Because I do actually have some diagrams of this happening. Okay, so we sort of know this already, because I think a lot of people will have tried this, that if we try to do something to one of the input variables in a function, it will definitely change the variable that is inside the function. This int number here is actually something that exists within these curly brackets, even though its name and declaration is kind of technically outside the curly brackets. It happens inside the curly brackets, and once we hit the closing curly bracket of the function, this thing will go away. So we made a change to this temporary variable that was inside the function, and then the function ends. It makes no changes to x, because it never had access to x. It only had access here to the value 5, which was a copy of the value that was in x. So when we do this printf, x will still be 5. It won't have doubled to 10. So this is the concept that when we give, and this isn't always going to be the case, right? Different programming languages do this in different ways. But C, and the way we're doing it, does this particular thing called pass by value, that when it goes into a function, it says you're going to get the value of the variable you put in there. You don't get access to the variable itself. Now we've worked with pointers now a little bit, so we know that if we wanted to, we could give a pointer to x, and then we'd be able to change it. Those are things like the swap function that I was talking about earlier, that where we can actually get access to things. Alright, there's a lot of talk in there. I'm going to let you talk amongst yourselves for a bit, because I think if I get caught up in that conversation, we won't get through the content that I need to get through today. Okay. So this one, I think I've showed you this diagram before, so this is a little bit of a recap of these things, because I need these clear in your head before I go on to the next concept. So, functions with pointers. If I give a pointer to a function, so here's my whole program's memory, and so my main function has a chunk of this memory, and it's created a pointer. When I call a function, and I give it a pointer as one of its inputs, it makes a copy of the pointer. So the pointer can access a particular variable. A copy of a pointer accesses the same variable. So if and I was using this example before, I have an address of, say, 1000 Anzac Parade. If I were to give you, instead of the address, I gave you a number, say the number 50. And I write that down on a piece of paper and I give it to you, and I say, there's your 50. You can make changes to it, and it changes to a different number. If I have a copy of that 50, mine stays 50 while yours changes to a different value. So when we have our own variables, we have access to them and we can change them and things. The difference is, if I have an address written down on a piece of paper that says 1000 Anzac Parade, you also have an address written down on a piece of paper that says 1000 Anzac Parade. If both of us follow those addresses to their location, we end up at the same place. So we end up with a situation where there's only one place in memory where this stuff exists, but we both have access to it because we both have pointers that allow us to get to that piece of memory. So everything still gets passed in by value. Even with pointers, it gets passed in by value, but because the value of the pointer was a memory address, they both give us access to a variable somewhere else. So we've sort of looked at this concept before. This is what gives a function access to memory that's inside another function. So memory that I've declared inside my main function allows me to, I can pass a pointer in like that, or I can go deeper into functions. So I can have one function, I think someone was asking about this, I can have one function that creates a variable, and then it calls another function with a pointer to that variable. That second function will have access to whatever that pointer was aiming at. So whatever piece of memory that pointer was aiming at. We're going to go into more of the subtlety here. I'm not going to go too deep into nesting. We can obviously nest functions, so we can call a function inside a function. The jumbler example that I did had the swap function, and the swap function was called inside the swap multiple, or the jumble function, which means I was trying to show you that we can call functions within functions, which should maybe, we'll see how we go, maybe be reasonably obvious, because our main is just a function. It's a very special function because it's the one that gets called first when the program runs, but it's still a function like any other function. And the main function will call other functions, and so that's your first level of things being able to call things of their own type, and then it can go further deeper. We go down that same rabbit hole where we can put C structures inside themselves again and again and again and get deeper into the point where we confuse ourselves. Okay, so the alternative to the doubling function that I did a second ago is let's do a double where we're given a pointer to an integer. So this is a pointer to an integer. Can I just, yeah, I'm just making sure that previous diagram was still visible with my face in the top corner. Abiram is talking about calling functions from themselves. You can call a function from itself. We're not going to teach this here and now. We don't teach this explicitly in COMP1511. It's something that we're going to go deeper into in other subjects later. It's called recursion. When you call you call a function within the body of its own function, and so you could have the doubler that then calls doubler inside the doubler on the same number, and that would call doubler inside doubler, and it goes deeper and deeper and deeper. And so you've got to have a way of making that stop at some point. It's nearly like a while loop where you need to figure out where it's going to end before you do the stuff in it. Recursion's like an inverted while loop. I'm not going to talk any more about this. I don't want to confuse people because it's not necessary to know about it in COMP1511. And we have so much stuff that we wanted to teach in COMP1511 as it is, that if we were to pack in every subject that we thought was really cool for first year computing students to learn, then the subject would be, I don't know, I'm trying to think how long I would want to teach COMP1511 if I really wanted to teach everything. It would be probably 20 or 30 weeks, I think. We would do a whole year just on COMP1511 if I was allowed to teach all the cool things that I wanted to teach. But no, we're not going to do that. We're going to allow you to move on to other things and do other subjects as well. Okay, so going back here to the function for this double pointer. So it's not doubling a number this time, it's doubling a pointer. And it has an input which is an integer pointer. And so here we can see that there's x, and then there's a pointer to x, which is called pointer x, which is assigned the address of x at the beginning. So this pointer is declared completely ready to go because it's assigned an address value when it's created. And if I give that address to this function, it's not going to be the pointer that's given to the function. Only the value of the pointer is passed in. However, the value of the pointer is still the address of the integer x. So if I say star num pointer, which says follow that pointer to its memory address, it finds this x. And it says, okay, that x, make that equal to whatever value we found in the x. So star num pointer also takes us back to x, and we get a 5 out of that. We double that. That is 10. And then we assign the value 10 to the end of this pointer, which is the star that takes us back to the x again, because we have the address of this x stored in this pointer that was then passed into this function, remains the same address even after it's copied. So what happens then is the x that used to be 5 gets doubled to be 10. So the way that this is all working, it's all usually easier to draw diagrams like this. So this is the double function that was given a copy of that pointer. It was given access to that variable by that pointer, and so it can change that variable. I'm always sort of going to go back and forth between diagrams and code and me talking and some text about it, because I think that there's many different ways to think about how pointers work and how memory works, and it's always good to have some visual guides for that as well, because it can be pretty confusing otherwise. Okay, I'm not going to try to follow a chat. I know that if in a different world, I would deliver these lectures over like a 4-hour block, and then we would stop and talk about all the things that's happening in chat, and I find it really interesting. It's actually kind of distracting for me, because it's like, I want to talk about that, but we're not going to for the moment. Yeah, I think in a perfect world, I would spend a lot longer and we'd get into conversations about things like that. But I think all these really cool conversations that are happening there, take them into your tutorial and your lab. I know that these are a little bit more awkward now because they're online, but I still think they're very much worth going to. So as much as you can, try to keep going to your tutorials, because there's a lot of interesting stuff to learn there. And especially those of you who are wanting to get into these discussions, your tutor is a really cool person to talk to about those sorts of things. Okay. Okay, so that's there. Now, arrays. Someone was talking in chat about arrays a second ago, and I wanted to point out the way that arrays and pointers seem very similar. So they seem very similar because the array is a variable. And the way that we were thinking of arrays was an array was a chunk of identical variables. But when we use the array itself, so when we use the array with no square brackets, what it actually gives us is the address of the start of the array. So the array variable itself is not exactly, but very, very similar to a pointer to the start of the array, because the array itself is a memory address for the start of the array. You can actually interchange it. You can, if you want to, you can create a function that is intending to work on an array that takes as input an integer pointer. And you can pass an array to a function that takes an integer pointer as input. I'm saying integer pointer because I'm just in my head using an array of integers. So if I had an array of integers and I had a function that took an integer pointer as input, I could pass the array as input to that function. And it would just be happily work on it, because the array would give it an address and the pointer input would be expecting an address, and it would just be totally happy to work with that. So here is this kind of secret that I needed to teach you a whole bunch of other stuff before you could get to this point, and the understanding that the array is very similar. It's nearly identical, functionally identical to the memory address of the start of the array itself. So the value contained in the array variable is the address of the start of the array. And this is why every time that we've done a function so far that has used an array, it has always had access to the array as it was in the main function. So instead of having this situation where this taking a variable in was unable to change it, the array actually acted much more like this one, where it was acting as if it was taking a pointer, and then it was getting access to the memory itself, because the array variable was actually the location in memory where all of the array elements were stored. So when we passed an array into a function, it was copying, it was still by value, but it wasn't copying all of the elements into the function. It was copying the address of the start of the array into the function, which gave the function access to the entire array. So this sort of, I think, is hopefully opening up your minds to how once we've put all these jigsaw pieces together, now you see this picture of why the array works like this. So now that we know how memory works, and we know how pointers work, I can say to you an array is just like a pointer. And that's how it accesses the memory. And that's why we can pass an array into a function. And the function makes changes in the array. We go back to our main, and our main has all these changes in it. It's not because arrays were special or different. It's just that arrays were passing their address into the other function. And so hopefully this answers questions, because people have been asking these questions, I think, earlier about the about passing arrays into functions. Tony was asking, how can there be an array without the square brackets? So remember, we can create an array with the square brackets, and when we use the square brackets on an array, we're finding a single element of the array. Because we use the square brackets, we put a number in there. That allows us to index somewhere into the array. If we don't put square brackets on the end of the array, we use it by name itself. That's us using the whole array as if it's a variable, and that's where we get this memory address variable. So anytime that you've called a function and passed an array into a function, you'll notice that when you pass the array into the function, so when you call the function, open your brackets and put the array in there, you don't put square brackets on it, right? So if you're passing a whole array into a function, you don't put square brackets. We've had a couple of lab exercises on this, so if you want to, you can go back and check on those. Whenever you pass the array in without the square brackets, that's just giving the address of the memory where the array is. Michael Ruffle, I'm just going to assume that's your real name, Michael Ruffle of the Ruffle family, has said, if the array is a pointer, which it kind of is, not exactly, but it kind of is, which is an address, that's the start of the array, but how can it recognize the size of the array? That's an interesting thing, and the answer is that it cannot. So, the array variable itself does not know how big the array is. And this is why we've been really careful. So we've showed you this in two ways. One way is we hash define the size of the array at the beginning of the program, and then we always use that as the maximum of how far we're going to iterate through the array, and we say we're never going to hit this size value because that's the index that's off the end. The other thing that you may have seen sometimes is when we have a function that works on an array, we pass in two variables. One is the length of the array, and the second thing is the address of the array itself. So there is no way that the array on its own can tell you how big it is, because the array on its own is just an address. And so that's, you're seeing that exactly, which is why we usually pass in more information. Yeah, DCC has warnings for if you go off the end of the array. If any of you are using your own computers and you use Clang or GCC, they may allow you to access from an array to indexes that don't exist. So you can go off the end of the array. Old school, right? Really, really old school computing. I think from back in the 80s, maybe it was still there in the 90s, but I can't remember. It was a while ago. You used to be able to read off the end of an array, and if you were careful about how you read off the end of the array, you could actually rewrite the code that was in the program. So going off an array allowed you to go somewhere else, which might get you into the actual main function, and you could rewrite stuff in the main function that allow the program to do something it wasn't intended to do when it was first written. This was the first hacking. So this is one of the ways that you could hack your way into systems, is to find a point where they were using an array and they weren't careful about it, and you could move the index of the array off into other code and then do things with it. Anyway, it's another story entirely. We do have some interesting stuff in the if you're thinking about hacking and cybersecurity and stuff like that. We have some interesting stuff in the lab this week, which is a first introduction into codes and ciphers, which some of you will have done, some of you will be doing this week, which is all about how to encrypt something. So how can you change something so it's not so easy for people to understand it? So how can you change a line of text so that it doesn't appear as it doesn't appear easily readable to someone, but if you know how to decode it, you can get it. And so we do some fun stuff in there. Oh, by the way, I don't know if anyone has started this or tried this yet. The final challenge exercise this week, it has all these warnings on it of just ultra hard challenge and stuff like that. One of our previous subject admins actually did do a full implementation of that, and it was more code than assignment 1. So that's something for if you dare or if you want to. It's super non-obvious how to do it. And this is really, really definitely the way that I was talking about the challenge exercise at the very beginning when I first introduced you to the subject. It is definitely not worth in marks the amount of time that you would spend on it. So just bear that in mind. You can totally look at it if you want to, especially this week when there's no assignment happening. But I mean, you might have assignments or other subjects, so do whatever you want to do. But that final question is really, really full on. It's actually like a reasonable code breaking question. So it's the kind of thing that people would do when they're trying to decipher secret messages between governments and stuff like that. Yeah. Okay. So back to what we're talking about. Abraham's asking, is crack substitution even possible without 1,000 lines of code? I don't know. I think you'd have to be writing really, really tight, super efficient code to get that done in under 1,000 lines. I can't remember how big the solution is that Andrew Bennett, one of our previous subject admins, did on it, because I think I can't remember. His solution might be under 1,000 lines, but it's definitely ballpark 1,000 lines. Anyway, we digress. We don't want to go too deep into everything. Okay, so back to what we're talking about. Arrays, because they represent themselves like the memory address the same way that pointers do, can be used interchangeably with pointers. And this is why that when we passed an array into a function, we always had access to the array elements as they existed in the main. And any changes we had would always go back to wherever the array was, and they would happen because of this situation, which we now sort of understand. I'm okay if not everyone understands this yet. We need to sort of spend some time with it. I've got some more slides that are going to talk about this, right? So, yeah, the array gives us access to the array elements regardless of whether they're in the function or not. Okay, so if I have a function called double all, which is going to take in an array of numbers, it is always going to have access to this array, because this input here, actually let's look at the function itself. So the function here is called double all. First variable it takes is the length of the array, second variable it takes is the array itself. So this bit is where it gets the address in memory of where the array is, and this bit is how it knows how much memory that array has before it goes off the end of it. So let's go back to the previous slide. I should check every now and then that my face isn't covering something up, so it's only if there's something up in that top right corner. Okay, we've got an array, we pass in the length of the array, so this could have been a hash define if I wanted it to, but for the moment, double all might be used in our program on multiple different sized arrays. So if it's potentially going to be used in multiple different sized arrays, I will often pass in the length of the arrays as a variable rather than just using the hash define. So length 3, here is my array, and so this is the thing that I can't remember who it was that was asking me. Tony was asking me about how we can have an array without the square brackets. So if I use the array as its variable, as its name, without square brackets, it means I am not trying to find a certain element inside the array. I'm giving you the whole array, which is exactly what's happening here. I give you the whole array, and I say it's of length 3, and run double all on it. So double all comes in through here. Basic while loop, so 0, I++ until less than length, which means it's going to look at every element of the array exactly once, and it's going to do that same doubling thing before, but this time it's on an individual array element. So we access an array element, times its value by 2, store that value in the array element. So this is going to go through 1, 2, 3, and when we do this printout here, it's going to say 2, 4, 6. So we're printing out like that. So this is just showing you that the array here can go into a function like this, and it will make changes to the array itself because of this situation where the array actually just had the memory address of where the array elements were. So we don't get a copy of this array. We don't get the pink array elements copied into the function. We just get the address of the start of the array copied into the function, and we can then make changes to the array. Okay. Next thing I want to talk about is what happens in our memory when our functions run. So we've got a decent idea now about what pass by value is. Pass by value says that new variables are created for the function based on the values of the inputs that were given to the function. So I've got some memory here, not to scale obviously, this is never to scale. And what happens to variables that are made when a function runs. So program's memory is a large chunk of memory where it's got a lot of space to do things, and our main function has some of that memory. The main function doesn't necessarily have all of this memory. It may end up using a lot of that memory, but it's a part of that memory. And so there are variables that are declared inside our main function. Got to keep in mind that every function has its own separate piece of memory, and every variable inside that function is inside that piece of memory. So this is like the curly brackets. So I remember when I said before, the Vegas rule of curly brackets, the Vegas rule of what we call scope, program scope, is what goes on inside the curly brackets stays inside the curly brackets, which means the variables are entirely contained within the memory that function is using. They don't appear somewhere else in the program's memory, they're just inside the function. Which means that when we call a function, the main function calls another function, this function will have its own memory. I mean, it's not even necessarily connected to this. It could be just somewhere else in the program. If we would do this to scale, the program would have all of this possible available memory, and then the main and that tiny function would do these tiny parts of it somewhere. But the important point is, when we call a new function from the main, there are variables declared inside the function. These variables include the inputs. So the inputs to the function are new variables that are declared by the function there, and they're wholly contained within the function's memory, and they're wholly separate from the function from the memory that was used for the main. So each of these have their own variables. When the function is first called, some of these variables, if they're input variables, might have exactly the same value as the variables that were passed in by the main function. But note the dividing line between them. They are not the same variables. Function has its own variables, main has its own variables. There's no connection between them unless, say, one of those variables is an address of one of the other variables. But we'll get into that. So, what happens when the function ends? So this function completes its work and it says return. Maybe it says return, or maybe it just finishes, because we've got void functions that just finish, and we have functions that have outputs that return. When they return, they might send some information back to the main, and the main can store that information in its own variables. But importantly, the variables that were declared inside the function disappear when the function is finished. So when the function ends, all of the memory that the function was using is just given back to the computer. So I could put something else in here afterwards, the program's memory. Well, the program could put other things in there, but that function's memory disappears, which means any variables I created in that function are no longer accessible. We no longer have any reasonable idea that we could use them again, they're considered lost and gone. People talking about line limits? No, okay. People are confusing each other with line limits. Abraham, stop jumping ahead. You're spoiling the narrative. I assume Abraham has seen a lot of C before in some way or another. But I'm glad that at least my lead up to things and my suspenseful lead up to things that is piecing together all the information for people to learn is making sense to you. That makes me happy in some way. Okay. So, function runs, function ends. When the function ends, the memory for the function disappears. All of the variables that were being used in the function disappear. This includes the variables that were used as input. So all of these copies of the variables we had in our main function disappear. If we have used pointers and we've had access to things in there, yeah, sure, they've still done something, but they disappear, and whatever changes in here still happen. I'm going to talk later about this as well, because there's actually even deeper ideas of the memory structure of functions as well. This is my simplified version that's going to get you understanding some important things right now. So, what if we want to keep that memory available? Oh my god. Don't you dare talk about Goku like that. That's oh. Sean said no one likes Dragon Ball. That's anyway, I'm not going to get distracted by what's in chat, but I'm going to say that Dragon Ball was, I think, for me, growing up, one of the most enjoyable things to watch, because, like, I remember working a part-time job, so I was only up to watch Dragon Ball, like, one day a week, and it was really funny knowing that there'd been, like, 5 or 6 episodes between the things that I watched, and there were 2 people in the same fight 5 or 6 episodes later, and like they just destroyed more of the planet that they were standing on, but the 2 of them, like, you know, they messed up their clothes, but they were still fighting and they're still yelling at each other for like 5 whole episodes, just one duel between 2 people. It's beautiful. It's the most hilarious TV ever. Okay, anyway, what if we want to create something in a function? So what if I say I want to do this? I want to have a function that says create array, and I want the return of this function to be a pointer, which means I want to give back the address of the array. I want to be able to say, I want the creation of this array to be off in another function where I don't have to have the creation of it sitting in my main function or anything like that. I want this off to the side. The problem with me trying to run this is I would return the location of this array. The downside to that is the location of that array is in this memory here. So it's in this memory that has been turned off. And since it's turned off, when I try to access that array, it'll say, no, there's nothing there. You know, this is where the function used to be. There's a memory address, it's a valid memory address, but there is no memory there that we're using. So I can't do this. I can't say, create an array for me. I will give a pointer back to the main function, and then I will end this array. I'll end this function, which does end the array. Once I end that function, the pointer is now aiming at empty space. There is no array there anymore. So I can't do that. I can't create something and expect its memory to survive longer than the function itself that created it. So in comes the idea of memory allocation. This is our capability now that we're adding to our toolbox of C, where we can say, I would like to create a variable, and I would like that variable to last the entire length of the program. So I would like to create that variable, say in a function, and say, this thing is going to be here for the whole program. It won't go away unless I explicitly tell it to go away. And this is 2 functions that we're going to use. These are C standard library functions. One of them is called malloc, which is short for memory allocation, and the other is free, which is not short for anything, it's just free. So what these 2 things do in a pair, malloc is going to allow us to ask the computer for a certain amount of memory. So we can say, I would like an integer's worth of memory. Or what happens much more often is we have something more complex than that, like a struct. So a struct, we don't always know exactly how much memory it has, but we're going to say, okay, I would like this struct's worth of memory because I'm going to store this memory, store this struct in this memory, but I want this thing to last longer than the function that it's in. I want it to last the whole rest of the program. So I will say malloc a certain number of bytes, which is exactly how much memory that we want to use. The smaller size memory we're going to use is bytes at this point. And this allows us to grab a piece of memory and take control of that piece of memory, which means that when the function ends, it won't be in the function's memory. It will be outside of the function's memory. It won't be part of the stuff that the function wipes away when it finishes. So, actually, little side note, the function doesn't actually wipe its memory away when it finishes. It leaves it there. So everything that was in that data is still there in the function, which means that sometimes if you can manage to find a pointer into where a function used to be, you can still read the old variables there, but you can't guarantee they're still going to be there once you start making more variables and using their memory again. It's a little theoretical stuff. Don't worry too much about that. Okay, so that memory will be assigned to us, and it won't go away until we say specifically, I do not need that memory anymore. So if I make a memory allocation of an integer or a struct or an array's worth of memory, I will say malloc to do that. And then the function can end and I will still have access to it, because malloc is always going to give us back a pointer to that memory. And so long as I have the address of that memory, I can always keep using it. You've got to keep hold of that address though. If you lose the address, then the memory is just sitting there and you can't find it again. So that's something we'll talk about later. So the memory will stick around longer than the function that it was in because it won't be automatically cleaned up, but we use free to clean it up if we want to. Okay, so here's a pictorial, I think is the right word, example of what malloc does when we run it. So we've got a main function and a function that was called by the main, and we call malloc. If we call malloc, we get new memory for something. So we can just say how much memory we want, and this memory will be outside of the function. We will be given a pointer. So it's outside of the function, we've got a pointer, which allows us to access this piece of memory. Now we can give that pointer back to the main, so the main now has a copy of that pointer. The function can end, but when the function ends, it cleans up its own memory. It does not clean up this memory that's outside of itself. The function can only clean up what's inside its curly brackets. So malloc is a really specific function that allows us to take memory that our program had access to that's not inside any function. Note that this is not inside the main function either. The memory assigned is somewhere else, which means that it's going to last and it's not going to get cleaned up automatically by any of these functions when they finish. So memory is still available to our main, which means that we can use a function to create something, then the function itself can go away, but the thing we created still exists. And this is the power that we get from malloc. We're going to be using this a fair bit actually in the near future. So in code, malloc is a reasonably simple function to use if we just remember that its input is how much memory it needs, and its output is a pointer to that memory. Now I'm going to show you a function which is going to be the only way we're ever going to use malloc in 1511, and I suggest that the majority of the time that you do any kind of explicit memory allocation, you use this function size of instead of counting up the size of something and writing it down. So if I wanted to, I could have an integer pointer here, and I could say 4, because this is in bytes. An integer is 32 bits, which is 4 bytes. So I could put the number 4 in here to memory allocate exactly the size of the integer. The downside to this is, what if, say, 10 years time, 20 years time, I don't know how long it's going to be, but the standard for integers changes from a 32-bit to a 64-bit integer. And we start only using 64-bit integers, not 32-bit integers, to the point where they change the spec for C. And these integers all require 64 bits of memory, and then my malloc is incorrect. However, if we were to change what the specification for an integer is, and I had put in size of int, size of is, it's not actually a function, if I remember correctly. It's a kind of a macro, which, because int is not an input that you could normally give to a function, it's a type, but size of can look at a type, and it can look at the type and it can say, this is how much memory that type uses. So size of a type, of say an integer, will say this is how many bytes the integer uses, and then you do malloc of the size of an integer, and this is the memory allocation of enough space for one integer, and you can put that in an integer pointer. So this pointer now has access to that new piece of memory that's created. So this is a trivial example because you'd never need to malloc a number, because numbers can just be passed around by values and things. So you would very, very rarely malloc a number to have this one number sitting outside your code. But we're definitely going to be mallocing bigger things like structs. Okay, so just remember malloc size of, this is the way we're going to use malloc. Nearly every line that we put malloc in is going to look exactly the same as this line. So it's just going to say, here is a pointer to a type, and we have allocated exactly that much memory of that type. So size of integer, and which means we're memory allocating enough memory for one integer with malloc. And so to get enough memory for one integer, we do size of integer, and then we have an integer pointer to aim at it, and it all just kind of fits together like that. Question from William: will malloc have any presence in our second assignment? It will have a huge presence in our second assignment. If you don't malloc in the second assignment, nothing will run. So we're going to be working very explicitly with memory in the second assignment. Not even next week. Tomorrow, I'm going to start talking about a structure called a linked list. This is all building towards the linked list, by the way, where we memory allocate sections of memory and we link them together in a chain. And that's going to be what we're going to be using as our main data structure for the second assignment. So the first assignment was a data structure which was arrays, so blocks of memory together with numbers in them, and we use two-dimensional arrays to make it interesting, to give you more things you can do. Also, because two-dimensional arrays are really easy for people to think about visually, so that was something that I use as training for complex arrays for people, because you could write it down on a big piece of paper and draw stuff on it, and you'd have a decent idea about what you were doing. Linked lists are harder, which is why they're the second half of the course rather than the first half of the course, because they involve memory manipulation and things like that. But we'll get into that tomorrow. Okay, so the other thing we need to do is we need to make sure that we use free. So we've got here malloc number. This is this thing that's going to create a number, and it's going to allocate the size of memory for it. This kind of creation function is something that's really, really common when we're working with structs. Because most of the time when we make a struct, we would push making the struct into a separate function, so it's not busy in the code, because especially it's going to get reused in lots of different places in the code, so you don't want your creation function or your creation code to be copied in multiple places. Usually it's in a function on its own. Which means that we need to keep track of these pointers, and we can make changes to these pointers. There could be a whole lot more code in here, and we want to make sure we're doing that. And then we want to make sure that we're freeing that memory, because if we're not freeing that memory, then that memory is still allocated to us, and we can end up using a whole lot of memory and forgetting to free it. And if we keep doing that, we end up in a kind of a situation where our program could literally run out of memory because we've allocated lots of memory and we haven't freed it, and then it just sort of gets stuck to us, and we don't let it go. Actually, I can show you that, because I have a code demo with the lectures today that is about memory allocation. I can show you some stuff about memory allocation there. But I think that I can't remember what. Yeah, we got a bit of stuff before the break, and we're actually going a little over time, so I should go to the break now. Actually, no, I'm gonna finish talking about memory, but I'm not gonna do any demos until after the break. Okay, so freeing up memory looks like this. Here we have allocated memory, something that I malloced before. So you saw the other one, the memory allocation before, and I've got a pointer to it. If I want to free something, I say, here's the pointer that aims at the memory that I'm trying to free. Please go to that memory and kind of not necessarily wipe it, but just say that that memory is no longer mine and something else can use it now. The trick behind this is, remember how we said pointers have types? So you can have an integer pointer. I could have a struct bender pointer, which we have used actually last week. If you want to go back to the live stream that we did, that pointer knows exactly how much memory it's aiming at. So this is a slight difference between an array and a pointer. Is the pointer knows all of the memory that's aimed at, whereas the array is just the address of the beginning, and it knows what type is of the array, but only one element. It doesn't know how many elements. Whereas a struct pointer knows exactly how big the entire struct is with all of its stuff in it. So when we free it, it goes over here and it says all of this memory that was being used at the end of that pointer. So in this example, it's an integer pointer. Here is now freed. It's no longer accessible to us. We're not going to be reading its value anymore, but it is now open for us to reuse for other variables. We can put other variables in that memory or whatever. And so this action allows us to give the memory back when we're not using it. And we have to remember to do that. Every time we memory allocate something, that's us grabbing a piece of this memory. And this memory can fill up if we grab too many pieces of it. So if we don't free it, this memory fills up and we stop being able to use it for other things. The term for this is called a memory leak. And I've got some information here about it. So every time we malloc, we free. This is me as I was talking about just a second ago. So size of tells us exactly how many bytes something needs. We're going to memory allocate something. We can memory allocate. We can call size of on any variable type. The only issue that we would have if we were allocating an array is you cannot call size of on an array. You would have to take size of a single element of the array and multiply that by the size of the array, how many pieces are in the array. But works very, very well for structs. So you can do size of a struct, and it will calculate how much size that struct needs, knowing all the stuff that's inside it, and it will just allocate a single struct's worth of memory. Everything that we allocate must be freed. If we don't free it, we start using up memory that we don't necessarily have. And that's called a memory leak, because if we let our allocated memory, if we lose track of our allocated memory by losing the pointer to it or something else like that, we end up in a situation where the memory sort of disappears. It's not accessible to us anymore, and we haven't freed it, so the program and the computer think we're still using it, because we haven't said we're freeing it. So the program just thinks, oh, you wanted to hang on to that, so it just hangs on to it for you, and eventually you can run out of memory. That's called a memory leak. We have a special flag on DCC called leak check, and you can do DCC with all your other options, like the file you're actually creating and stuff, and then call leak check. And then what that's actually going to do is let you know if there was any memory at the end of the program when it finishes that wasn't cleaned up, and it will remind you that you should have cleaned all these things up before you left, because there's all this memory still attached to the program. Okay, so gonna go on break. So longer first half than second half here, but that's okay. I think there is more stuff in the first half. So it's easy to forget what you've allocated. So this is the thing that's always interesting, is you need a sort of an awareness of what your code is doing. This is the kind of thing that's going to come with time. It's going to come with training and practice. But we always get into these situations. We always get into situations where we allocate memory, and then later on we forget to free something. And then the longer our program runs, with allocating memory and not freeing stuff, the more this kind of build up of memory happens that doesn't get freed properly, and then it ends up in this situation where we start to lose our memory. Like the longer something runs, the less memory we have for other programs, the more memory this thing seems to just be eating. And that's often because it was actually losing memory, and it wasn't capable of continuing running because it had allocated all this memory to itself and then just wasn't even using it. Older versions of Windows used to do this. So this is where that whole idea came from, that people used to go, have you turned it off and on again? Because literally older versions, not just Windows, other operating systems did this as well, where there were memory leaks in the code for the operating system. So the operating system would start off when you first ran it, it would be taking, I don't know, 100 megs of memory. And if you left it on and running for a week, the thing would be taking like 500 megs of memory. It would be doing the same things it was doing before, but somehow it would be taking more memory. And you keep it going, and it would be taking more memory and more memory. Just because somewhere in there was a small memory leak in an operation that kept going again and again and again, and then the program would just take more and more and more memory until the computer would just crash. You get a blue screen, start it up again, and then it'd be on its small piece of memory again, and it would just sort of grow. So we want to be careful that we don't have memory leaks. We're sort of training you now in situations where the memory leaks are not like the ramifications, the sort of fallout for having memory leaks isn't that bad right now, but it will get worse the longer your programs try to run. And so for the moment, all of our programs are running for like a second and then stopping. Not even a second, you know, they're just running and stopping, running and stopping. Or they're running, waiting for input and stopping. When you get deeper into a programming career, you're going to start writing things that are, say, server-side things that are running for months at a time. You have any memory leaks in something that's running for months, then wherever it's running, it's going to start eating memory. It's going to start eating so much memory that it's all just going to fall apart at some point in the future, and you can't always know when. So we want to be really careful. Every time we allocate memory, we want to make sure we free that memory later. And so this requires just a little bit more awareness of everything that we've created to make sure that everything that we've created, we let it go before we're finished. All right, so let's go on break. I'll try to make it a quick break, so it's about 10:15 now, and so we will come back at 10:20, and I'm going to talk about multiple file projects. If I have time, I might show you a memory leak as well. We'll see how we go with that. All right, cool. We'll break for a little bit. All right, I'm back. Oh, I should move my face. I said I had no visual memes, but I did have just this one. Did that work? Did that work? Okay. So, Olvesta, I thought I didn't have any memes in today's lecture, and I think it's because I'm such a meme lord that I forget that I've got memes, because I've just got so many memes, and they're just coming out all the time. Okay, so let's get that back out of the way. So that meme says, I have no memory of this memory allocation. Get it? A bit of the Lord of the Rings. Hopefully I don't spoil too much stuff for people with these memes. I would hate it if the cool stories that there are out there in the world, I'm spoiling a whole bunch of them with the memes. But I usually, like, most of my memes are either from movies that I watched when I was a bit younger. As in, like, Lord of the Rings is, what, 20 years old now, and I still love it. And last time we had lectures, like week before last, I did a meme from Aliens, realizing that Aliens came out in, I think, 1986. So I think at that point where I delivered that lecture, I was the only person who was actually alive when that movie was out. Unless there are people here who are mature age students, which is totally fine as well. Maybe you are also there, but who knows. Cooper's like, if people haven't seen or read Lord of the Rings, it's kind of their own fault. I mean, that is kind of a fair call, because Lord of the Rings is like kind of one of the most iconic um, books and film series of all time. So, you know, you kind of can't go wrong if you haven't seen them or read them. Anyway, on to actual code. Okay, so I want to talk about C projects with multiple files. Yeah, we're gonna. So I also did want to show you some memory allocation stuff. So let me just check out VLab. Okay, here's a memory demo, and this is the same stuff that was in the slides. Oh, I didn't want that email address there. Doesn't matter if I change it here, because the version that you've got's got that address. That's my personal email address. Please don't email me about 1511 stuff on that address. Like, when we do stuff 1511, there's actually a team of us looking at that, and I prefer you to email the team in case I'm too busy to answer your email. Anyway, okay, so here's our ability to create a pointer to something and then manipulate that pointer. So I just wanted to quickly show you. Everyone's laughing that I left my personal email. I mean, it is my public UNSW email address, so it can be used. I just don't like it to be used for the subject, because I'm not the only person responsible for the subject. I have other people also working on the subject, and I want them to see those emails as well, so that we keep track of everything. If you send emails to me, like, just imagine like 700 people all send emails to my personal email address, which is kind of what happens sometimes. Every now and then, when I take more than one day off at a time, my inbox just gets flooded. So I don't want your important emails to get lost in that, which is why I like people to send emails to this address for the course, so that I have someone else reading that to tell me, Mark, you didn't answer that email. And it's like, yeah, I'll get to it eventually. You know? So I apologize also for everyone who's been emailing me, especially recently with all of the subject upheaval, because my backlog is taking longer than it used to. I think I'm like a week behind on some emails or more. I apologize. Anyway, memory allocation. Back to memory allocation here. So this is us allocating a variable, and then it runs. So if I was to just compile this memory demo.c, I'm just going to call it memory. Oops. Ooh, what's missing here? Oh. There. I am missing a semicolon. Oh, this is another one of those past mark things. There's a whole bunch of stuff missing in this. This is quite interesting. I think I intended this to show some debugging, but this time I wanted to go quickly on it, because I know I've only got half an hour left for other stuff I want to talk about. So I'm going to say also that one cannot call malloc here if it doesn't know what malloc is. So there definitely needs to be some hash include here. And I'm just going to, rather than looking it up, I'm just going to say that all the memory stuff is in the standard library. So standard lib.h. I haven't even included standard IO here. Alright, so I'm going to compile this again, and hopefully this will work. Okay. Now, let's just run it. We're not going to see anything, because there's nothing happening here. But, let's compile this again with our special flag that we can add on to our DCC thing called leak check. Leak check is going to tell us if there were memory leaks or not. So if I run it and it ends, there's no memory leaks, that's fine. Let's try putting a memory leak into this by not freeing something. So we created it with malloc, which means we've allocated memory and we haven't freed it now because I've commented out the freeing. Let's have a look at what happens. I'm going to compile that again. I'm going to run it. Ooh, error. Free not called for memory allocated in malloc in function malloc number in memory demo at line 21. Line 21 is here. So here's where it was created and I didn't free it somewhere. So leak check's really handy. It can just sort of go through for us and say at the very end, these are the things you didn't clean up. So you've come in here, you've messed up this memory space, you haven't cleaned up after yourself, and that's an annoying thing. So please don't do that. Okay. Let me show you something else. So I was talking about memory leaks, right? And in talking about memory leaks, it's hard to see what they can do. But let's have a look now. I can show you how we can create a memory leak by doing something like this. Okay. So I hope. Oh my god. I should advertise Raid Shadow Legends. Everyone should like, comment, and subscribe. Don't do that. You don't have to. This entire channel is not monetized at all. In fact, if anyone sees ads on this channel, please let me know, because I think I've made this intentionally, so it's not. I'm getting paid by the university. I don't need to make money on YouTube. Although, what would be really funny is if there are people who are here who aren't part of the course, and I'd be kind of like, how are you even finding this? Like, it's not even really listed as learn how to program from scratch or anything like that. Oh my god, Milkshake Gamer, like, no, all of you stop. I've never played Raid Shadow Legends, but I've heard way too much about it. Okay. So, this is a very, very bad loop. Okay, so the golden rules of loops is no one should ever create a loop without knowing how it's going to stop. I've created a loop that just simply cannot stop because I put a 1 in the while question there. So this question can never be false. So this loop's going to go forever. But I'm going to do this to prove a point. I'm making a new pointer, and I'm allocating a number, assigning it to that pointer. Then it hits this close brackets. The pointer will disappear, which means that I have immediately lost track of the memory I just allocated. There are ads on other UNSW channels. Maybe the other UNSW channels have forgotten to turn them off. Who knows? Stop it, all of you. Okay, we're in a lecture here. Which actually, see, this is the funniest thing is if I actually look at all the text there, that would be like letting you all talk during the lecture, which I'm gonna try not to do. Okay, so this loop's super dangerous, right? So you can see what I'm doing here with this already. I'm allocating memory, and I'm immediately losing track of it because the pointer gets the pointer ends here, and then I override it. In fact, this code here doesn't even run. It's not going to work because that pointer doesn't last outside the curly brackets. So I'm just going to comment that out. This is going to keep allocating memory. So before I do that, I'm going to just make sure there's space for this over here. I'm going to use this other function. You won't really need this that much, but it's a Linux program that allows me to see what is using the resources on my computer, so CPU and memory. At the moment on VLab here, I am not using much CPU or memory. XFCE is the window manager that we use. Gedit is in there. Bash is the terminal. Oh no, wait, sorry. XFCE terminal. There is the terminal that we're using here. These two terminals. So I'm not putting very much load on our system at the moment. Not much is happening. So let's see what happens if I run this code that starts allocating a whole bunch of memory. So I'm going to save that. I'm going to come over here. Oops, what have I done? Warning unused variable. That's okay. Error, use of undeclared identifier. Okay, so I have accidentally tried to free it here. So because it's in here, I can't reference any of it outside here. So let's try this again. Warning unused variable, that's fine. I'm not using the variable. In fact, because this is a demo, I'm intentionally losing the variable. With a warning, it will still compile, but I suggest that anytime you got a warning, you probably shouldn't even bother running it, because you really want to get rid of those warnings. This one's trying to tell me something quite useful. It's like, you created something and you never used it, so why would you bother creating it? So I'm bothering to create it to show you something. So let's run this, /memory. I've pressed enter. It's in its infinite loop right now, and let's have a look at what's happening. So this is the program memory. It is now currently using all of my CPU, and the memory percentage of what I have available is slowly going up. That's gone to 5.5 gigs of memory. Wow, this is how much VLab has so much memory. Oh, 7.5 gigs. We hit 7.5 gigs of memory there. Just in that amount of time of me just allocating stuff. And notice it's gone. Let's go back over here. Killed. That's what I got. So what my program has done is it's just used more and more and more memory. It's leaked memory at an incredible pace, and it got up to, I think the last we saw was 7.5 gigabytes of memory, which makes me think that on VLab, the maximum amount of memory we're allowed to use for a single program is 8 gigabytes of memory. And so at that point, when I tried to allocate memory when I had used up all 8 gigabytes of memory, my program just gets completely removed from the computer by the operating system, saying you tried to get more memory than your limit of 8 gigabytes. So that's it. Thank you very much. Goodbye. So what we did there is we showed an example, a really, really extreme example of a memory leak, where we were allocating memory, we were not freeing it anywhere, we were losing track of it because these pointers were disappearing every time we used it, and that happened again and again and again. So these were only like 4 bytes at a time, you know, size of int. So 32 bits at a time, but it just went so many times that within the space of me talking about it for 10-15 seconds, this thing had used up 8 gigabytes of memory and just been told, no, you stop, you can't have any more memory. So I just wanted to show you that's what happens in an extreme example of memory leaking. Your examples of memory leaking are going to be much smaller than that in the second assignment and in lab exercises and stuff, but we do still want you to make sure that you can write a program that doesn't leak memory. Okay, so jumping back out of that, back to the slides. Don't worry, William, you can go back. Yeah. So there's a lot of people seeing this. Like, it's quite interesting, isn't it, when we burn all our memory like that. So C now gives you, we've now given you the capability to use your memory. With great power comes great responsibility, obviously. So you want to be careful with how much memory you use and careful to give back the memory that you finished using. So every time you memory allocate, somewhere else in your program there needs to be a matching free that then says that I want to give back that memory now that I finish using it. Leak check will help you find those as well. Okay, so other stuff I wanted to talk about today. I'm going to have to rush through this a little bit at least. Although I know that this topic was small on the memory one. I wanted to spend more time on the memory one. But C projects with multiple files. So we've already been, to a certain extent, using multiple files by using hash include. Hash include allowed us to grab files that other people have written for C, but now we're going to talk about including our own files. We're talking about building a project that has multiple files and joining those files together to compile them into one executable program. One of the nice things about having multi-file projects is it allows you to compartmentalize things. So I can have a file that has all of the stuff about a specific part of my program, and I know that if I want to find code on that specific part of the program, I go there and look at it. The other reason is we might even reuse parts of that program in other programs. So for example, I can have a program that I can run that does something like Minesweeper, but the minefield itself has its own separate piece of the program. So everything that I do that is in regard to the minefield and squares and stuff like that will be in one part of the program, and then another part of the program will be like, here is the game, so here is the interface that's shown to the user, the game loop that takes the turns and counts the time as people are clicking. This is more than you'd actually have in your assignments, unless you've gone full Hall of Fame on us, which is totally cool if you want to do that. And we could separate those things, and then I know that anytime I want to make changes to the board, it would be in the board bit. And then anytime I want to run the game bit, it'll be in the game bit, and we can separate those into different files. Things get more organized when we start doing that. Okay, we now have multiple types of files. So I'm now splitting into two types of files. One of them is called a header file, and the other is called a C file. So note that everything that we've been including had a .h on the end. And I'm pretty sure that someone asked me a few weeks ago, why is that thing a .h and not a .c? And I'm pretty sure I dodged that question because I said, I'm not ready to explain that yet, because I know that I don't want to explain that until we've learnt more about this. We've learnt about using C libraries before I explain to you the difference between the H and the C. So, the header file is nearly a human readable file. It's nearly, not always, but it's a human readable file where we can say, this is what this code is capable of, and it will usually have a lot of comments that people can read that code and go, okay, this is what capabilities are being presented to us in this file. So we've actually kind of been doing header footer stuff already. So you know at the top of our file, we have our hash defines, and we have our function prototypes and stuff. That's the stuff that goes in the header file. So the header file says, I have some functions. I'm not going to tell you how they work. You don't need to know how they work. We're just going to tell you how to call those functions and give you some information about what they do. That's all we're going to give you. That's what the header file has. The C file is what we call the implementation file, and that has all the messy code. Or not messy, try not to make it messy, right? Still human readable, but not necessarily at the level of the H file. But it has all the code in it that actually runs. So the difference between the two of these is the header file just says which functions you can call, and the C file has all of the code that's actually in the functions. I'll show you an example of this. I've got it downloaded already on my computer. So, or not my computer, it's in VLab. So I like to show you stuff in VLab because it's going to be the same way that you're going to be working with things. Let me see what people are talking about. Ooh, someone did randomized minds. Thank you. That'll be fun. There have been a lot of Hall of Fame submissions, and thank you for those of you who did. If you didn't, thank you also, because so long as you're doing the assignment and you're learning stuff from it, that's what we like. But we'll probably be doing a bit of a show off of the Hall of Fame things. I have some of the tutors working on the the actual view of the website of the Hall of Fame, which ironically I've never actually gotten going before because we always got too busy and never actually displayed Hall of Fame. So the previous Hall of Fame people have no fame at all. You may be the first 1511 cohort that actually gets a proper Hall of Fame up on the website. We're nearly finished with it, so it should be up soon actually. Okay, header file, as I was saying before, shows you what the code's capable of, and they show you how you can use the code if you can see it. I'm going to introduce a new keyword here as well called typedef, which is type define, which allows us to, and this is not that different from something like the hash define. Hash define was like pure text replacement. So it was like, this constant is this number. Type define is the same thing for types. I can say I'm going to make a new type, and it's not the same as a struct. So a struct was defining your own variable type, but that was like the underlying part of it. So defining your own variable type in a struct is saying, I'm going to use this much memory, it's going to have an int in it, it's going to have an array of this stuff in it, it's going to have some characters and strings in it, you can say what's in it. The type define just says, I have made something and I'm going to give it a different name. So we can often do this so we don't have to keep using struct something. I can just do type def, this is now my own new type, and then we can use it as a single word type, the same we use int and double and stuff. I'll show you how that works in a second. What we can do then is we can do some really interesting things where we can stop people from accessing the fields in our struct. We can give them a type define so they have a specific thing, and so that means that anytime someone wants the data inside my struct, they can't get direct access to it. What they can do is they can run some functions that I've given them that gives them access to this only within a safety net of how I have said the data in my struct should be accessed. So when we can split things into multiple files, we can put a wall between the files and say, you cannot get to this file in certain ways. In certain ways I have given you access to this file, but I can protect the data that's in there so that you can only access it the way that it's supposed to be. So I'll show you how that works in a second. I'm actually going to go over this again in the future, but I wanted to at least show it to you now when I've got a little bit of time. Okay, C file has all the stuff in it. So the C file is like the bottom half of our code. You know how we have all the functions at the bottom of our code, and they've got all this messy code in it that you don't always want to read to be able to understand something. That's what's in our C file. So the C file will actually include the H file. So it will include the header, and this is what connects those two files together. So the C file needs to know what all the functions are going to be before it compiles them. So that's why it includes the header. The header does not need to know what's in the C file, because in the compilation process, all of the stuff that turns the C into stuff that works will link back to the header eventually. So the header file doesn't need to know. I'll show you an example of this in a second. So the C file has to, if it's going to include the header, it should implement all of the stuff that was there. Actually, let me just at least show you some of this. So I'm just going to blanket open all of those and get rid of the memory demo. But here is my first look at multi-file projects, which has a person.h and a person.c and a main.c. So the main.c hash includes the person.h, and note that when these are our own files, they're in double quotes. When they're a library, like for example the standard input-output library, the angle brackets tells us that we don't have it, but our compiler has it somewhere. The double quotes tells us this is my file. I created this. This is my file. You should look in the same directory that we're compiling in to find this. So I don't need the standard input-output there, especially because I think person.h might have it already. No, it doesn't even have it. Okay, so we have no printout. Where does display person do it? Oh, display person has standard input-output in it. Okay, so this is where the includes here are just being used in the C file, and so we only need them there. So the example I've got here is the Batman example, but let me go through and show it to you first. Yes. Um, Batman's superpowers, one of Batman's most important superpowers is the voice. Anyway, we'll get to that in a second. So the Batman example is specifically because I was doing stuff with other examples, Avatar and I think Ninja Turtles and stuff like that. And one of my students said, "Can you do Batman?" And like he actually drew the bat symbol on the board behind where I was going to lecture before I got in one day, and I was like, okay, fine. And I changed this whole example to Batman, so it gets to stay in the course because of that, because I enjoyed that. Okay, so the C file has the implementation of things. So the H file, as you can see, has some hash defines and it has some functions here, but it doesn't have any of the actual code for the functions. It just tells you what it can do. Here's that type def that I was talking about before, the type define. So type define struct person pointer person. So struct person pointer is a type, and I'm going to use capital P person in place of struct person pointer. So it's nearly like these two halves of this piece of code here. Ooh, I'm dragging it. These two halves of this type define will now be the same thing in this program. So I can say person here, and this is where we use a capital. So the capital is for these particular types. And this is why all of our variables and all of our function names always started with a lowercase letter, because the capital P was something we were going to use for these particular types, and this differentiates them. So I have a struct person somewhere in my code. This file does not know what it is. It has not hashed included or anything like that. All it knows is that it is going to use a struct person pointer. So it's going to use a memory address somewhere, and that memory address is going to be called capital P person. So just between those two, you've got this situation where instead of using this pointer, we're going to call it something else, and that's just going to make it easier for us to know what it is. So we've got a type, which is a person, and that person can be passed into certain functions. To create them, we get one back, we can free one, we can add powers to them, and we can display them, that kind of thing. We don't know how this is working when we're using it in our main. We're just going to use them with their inputs and outputs and hope they work. This is exactly the same as what we've been using for stuff like printf, scanf, and other things. We're just trusting that that code exists somewhere and works, and all we did when we were using it is we grabbed the H file. We didn't even know what's in the C file. We don't even know what is happening in there, but we trust that it works because we've seen the H file and it has inputs and outputs to these functions that we just use. If we want to delve deeper, we can see this display person takes in the actual struct, not the capital P person, because what it does in here is it then accesses the things that are inside the struct. So one of the coolest things about this is I can give a person powers like this, and you can see my main. I've got Christian Bale. Not Christian Bale. I've jumped. Oh, I just gave away the punchline. I've got Batman here, and I'm giving Batman his superpowers. So he has the power of ninja. He has all his tech gadgets. He broods a lot because Batman broods, and if he didn't brood, he wouldn't be Batman, so I consider that one of his powers. And the most important power is the gravelly Christian Bale voice, which is what makes everyone scared of him. So if you can do that voice, then people will be scared of you. So I'm calling these functions, and I'm expecting something to happen to this person Batman that I've created here. I don't even know how these things work. And another thing that's interesting is I can't do things like this. Batman. I know that Batman is a pointer to a struct. So what if I go name equals, oh, that code's not even going to work anyway. So what if I use a string copy? Batman name spoiler alert, I've just tried to replace the name Batman with Bruce Wayne. And I'm like, you can't just give away his secret identity like that. Like you can't do that. Like that's just like that's horrible, right? So the interesting thing is this doesn't work because my person here and the person.h that I've seen, the only thing I know about it is it's a pointer to something. The struct is not available to me. I do not have struct person. Only person.c has struct person. Person.h does not have struct person. It only just knows it's a pointer. And main.c definitely does not have struct person, which means I can't access it. And this is like one of the most useful things about splitting things up into multiple file projects is I can't do the spoiler because the struct person is protected inside its own C file where I can't see it or I have access to it. All I can do is use the functions that are here in my H file, and using these functions I'm limited to what I can do. So this is a way we can program safely so that no one can corrupt our data by accident by going in and like just blurting out who Batman is. Sorry, spoiler alert to anyone who doesn't know this. But I mean, again, if you don't know who Batman is, it's kind of like the worst kept secret in comics. It's not even a secret, really. Anyway, so I'm not able to access this field. I don't even know if that field exists. Does it exist? It does exist, right? But I'm not able to access the field Batman name because in here I did not have that capability. If I wanted to, I could create a person and give them a name, but I have been given limited access to the data that's in that struct. I guess that struct is being memory allocated somewhere and things, but when I create it, I have to ask the H file if it knows how you can create it, and if it does, it gives me a pointer, and then I can use that variable that I've created in things, but only in the ways that it allows me to. So I can free it, so I can say, okay, give everything back, I don't need it anymore. And I only had two options. I can give it a power, or I can display it. Those are the only things I was given, which means I was not able to actually jump in here and change the elements of the struct. I was being asked not to. I was being asked to only use these functions to get access to it. And so this is this wonderful thing that allows us to protect what we've got in our data, and also allows us to give easy access to it, where you go, all right, just call this function and you'll be able to make the changes you need, instead of, okay, have to remember that this field means this and this other field means this and all that kind of stuff. Instead, what you would do when you want to give someone a power is the code in here to check whether they have reached the maximum number of powers and stuff, all that other stuff that happens is all protected in the C file, and in the main file you just ask if you can do it, and it will provide what it needs, but it will make sure that every time you try to make changes and stuff like that, it goes in the right way. Okay, I need to skip forward to talk about other things because we are running out of time. So the main file can include the H file, but when we compile these things, we want to compile all the files together into one program. So when we compile, we're going to compile all the C files that we're going to use in the program. Remember, and this is important, the main function. The main function is where our program starts. We have only the space in each program for one main function, because if we have two functions called main, then we don't know where the program starts. So we want one function called main somewhere, and that is exactly one main function where the program is going to start from, somewhere in the C files. You'll note that we had a main.c in our set of 3 here. That's just us being very, very polite to whoever might use our program and saying, you know, you probably want to know where this thing starts. Here is where it starts. The main function is in main.c. It would be like a horrendous troll thing to do, to have a main.c file and not put the main function in it. So we try to be nice to ourselves and other people use our code, right? Main.c, main functions in here. This is where you can find where the program starts. So we want main.c. once we compile, the program will start running from wherever the main is. It will have access to all these other functions that's in the C file, but where it actually starts executing line by line is from the main. You only need to compile C files. You don't compile any of the H files, because any header file that's being used in the program to link things between what's in the C files needs to be included. Because if you don't include it, you can't use it. And if you compile things without including H files, they're just separate functions, and you don't have access to them. So when we do a compile function, okay, so we're looking at the project. Did we have... Yeah, I'm going to jump forward here to the compilation, because I've already gone through some of that and told you about that. Yeah, this is how we would compile this program. So recall that our normal compilation command just has our C file and then the output file of the thing we're compiling. When we're compiling something with multiple files in it, we need to put all the C files that we intend to compile together in the one compilation command, and that will make a single program using all of those files. Where are we? Here. So I've got a little bit of time left before I need to finish. Let's at least compile this program and you'll see it running. Oh, wait. I can't compile it if I've got that line in there that I'm not allowed to have. Okay, I'm going to save that. Again, come across here, and I'm going to DCC. So, I know my main.c is definitely one of the files that I need to compile, but in order for that to work, it's including person.h. Person.h requires these functions to be implemented. They're implemented in person.c. So I need person.c to be compiled as well. The output program that I want from that is, let's call it person demo. I think that's what I called it in the other one. And that's going to compile that. I'm glad I didn't actually throw errors in that to show debugging, because I've only got like 2 minutes left to show this. Oh, cool. Michael's been answering some questions. All right. And if I run person demo, it says name Batman, powers none. So what did our main function do? First, it created Batman, and then it displayed that Batman has no powers. And that's exactly what Superman thinks about Batman. But then we think that Batman does have some powers, although most of his powers are just kind of a result of training. So Batman, we added the power of ninjutsu, tech gadgets, and the most important was the ability to brood on rooftops and speak in a gravelly Christian Bale voice to scare people. And then we displayed Batman again, and we got this new display that has the list of powers here. Note that in our main, we don't even know what's happening in those functions. I've even actually kind of half intentionally not really shown you those functions, but I've shown you how we trust the crossover between the H file and the main that says I'm just going to use those functions and they're going to happen. So swapping back over here, in 1511, we're going to keep these reasonably simple. So they're always going to be in this kind of format. There's going to be a C and an H file, and they're going to have some representation of something and some functions you can use in your main. We're not really going to go deeper than that and have multiples of them. We're not going to have them using each other, which they can. But assignment 2 will definitely be a multi-file project. So in, I don't know, 6 days? Is it 6 days when we release assignment 2? It won't be a single file like Minesweeper was. So it won't be minesweeper.c. It'll have a main.c, and it will have some assignment files, .c and .h in there. So I wanted to show you this, so at least you had an idea about how this thing works before we actually throw it to you and get you to use it. Oh wow, was there a whole talk about Batman going? Anyway, that's okay. You can talk about Batman if you want. Yes, Batman is highly problematic. It's like a billionaire beats up people with mental illness, and it's like, hey, hang on, that's he. Is he the good guy? Anyway, let's not go too deep into that, because we should wrap up the lecture there. So, what did we learn today? Things to go back on to think about. We're obviously going to put a lot of this stuff in the tutorials and labs as well. Functions in memory. learning how functions work in memory. I think that was something important. A lot of the theory behind what was happening in our programs was useful for us to learn. Learning about how to allocate memory and how to free it up later. This is going to have much deeper ramifications as we go on. I should also go in here to person.c and show you how we did this. So we had a struct person here. When we were creating one, we could do size of struct person. So this allowed me to allocate exactly the amount of memory I need for struct person without me having to count up how many bytes I was using, because I think there's a two-dimensional array of strings here. So, oh no, it's just an array of strings. And there's a string and an array of strings and an integer, and I'd have to count all that stuff up with the hash defines, and I don't really want to do that. I just want size of to happen here, because I don't want to count that up and put a number in my malloc, because what if I decide to change the length of these strings? But yeah, so this is that same kind of malloc thing that we were using, and free person here was also freeing, and I'm not even sure, were we freeing? Yeah, we were free. So if I was going to run this with leak check, I would probably get some information back out of this as well. Okay. So that's a bit about how we're tying together our use of memory that we've learnt today into also the concept of multi-file projects. All right, I'm going to wrap it up there because we're 2 minutes over now, and I don't want to go too far over because I know there's a tutorial lab that's probably starting on Blackboard Collaborate right now, so I should wrap this up here. Thanks for coming, everyone. I apologize I didn't sort of leave any time for questions. But what I might do is, okay, so anyone who has to go to their tute now, please go to your tute now. Anyone who wants to stick around and ask a couple of questions, I will have a look at what's happening in the chat right now and answer a few questions, the same way I would stick around at the end of the lecture. So I think there is already some active conversation going on there, because I think Abraham is answering some questions already. That's awesome. Abraham, you're like the unpaid helper in the lectures. That, yes. You can go back over the slides if you need. Ask questions on Ed if you want more information about these things. You can also definitely go have a chat with your tutor if you want more information. Next week, obviously, in the tutorials and labs, we're always going to follow up on things with some more stuff. So next week, we're definitely going to use some structs and memory allocation because I think that's important. Okay, so I was just going to see if there's any questions. Cheers to myself, Abraham, and Michael. No worries. That's what we do. Ask UNSW for payment. Yep. So if anyone has any questions now, while I'm sticking around, but obviously if you have your tute now, go to your tute. You can ask your tutor these questions as well. But if anyone has any questions, I'll just check chat for a little bit. James, there is definitely a tute now. I know that there are 2 tutes that... Is it 2 or 1 in this time slot that that happened just after the lecture? I mean, personally, I would not normally want to sign up for 5 hours of one subject in a row. But some people do. I mean, like, especially if you've got a long commute, it's like one of the most convenient ways to do it. But now we don't have commutes anymore at all. Okay, looks like we haven't got any specific questions, so thank you all for coming along, and good luck with the assignment 1s. We're starting the marking process pretty soon, and I will see you tomorrow at 11, and we will be adding in a little bit of information about command line arguments. I'll talk about them later, and also we'll be continuing our work with this idea about allocating memory using structs and using pointers and things, because we're going to start taking everything we've learned and building them into things. But, you know, we'll talk more about that later. Okay, see you all soon. Oh, wait. question is, when is the assignment 2 brief going to be streamed? So there was actually one question there from Matt, the radar technician. There isn't a stream for assignment 2 yet, but I will stream after I've released the specification, because I don't want to stream before I've released things, because I prefer that you have the documentation to look at while I'm talking about it, rather than me talking about it and it's kind of vague and you don't know the specifics of it. So that'll happen next week. Did